Welcome to the problem-solving set on mapping genes using recombination data. Question 1. The loci for genes G and G are 20 centimorgans apart on an autosomal chromosome. A homozygous dominant individual is crossed with a homozygous recessive individual. What gametes can the F1 individuals produce and in what proportions? So the cross that they mentioned in the actual question, those are the parental generations. So they're saying that D and G are in fact linked. They're 20 centimorgans apart on a chromosome. So let's draw these genotypes with linkage. So it's big D, big G on one chromosome, big D, big G on the other. And you're crossing that with a little d, little g, little d, little g. So even if crossing over happens when these parents are making gametes, because they're both homozygous at both gene loci, then the gametes are still going to be the same. So that means that you can only get one F1 individual. So that would be big D, big G on one of their chromosomes, and little d, little g on the other. So now it's saying for these F1 individuals, what gametes can they produce? Now remember that gametes can either be parental or recombinant. So the parental gametes come when there's no crossing over happens. So it could be either big D, big G, or little d, little g. The recombinant gametes, those come about from crossing over, which would happen right here. And that, again, happens during meiosis. So the recombinants would be big D, little g, or little d, big G. Now it's saying in what proportions will these gametes come about? Well, the two genes are 20 centimorgans apart, which means there's a 20% chance of recombination, and therefore the recombinants will make up 20% of the gametes. Because there are two different recombinant gametes, that means that each will occur 10% of the time, or 20 divided by 2. Now if 20% of the gametes are recombinant, that means that 80% are parental, and because those are 2, you divide 80 by 2 and get 40% for the other two gametes. So that's the answer for A. Now it says for B, if two F1 individuals, remember the F1's right here, two F1 individuals are crossed, what are the expected proportions of phenotypes in the F2 generation? Assume complete dominance for both genes. So that's saying that big D is dominant to little d, and big G is dominant to little g. Now because these genes are linked on the same chromosome, I think that the only way to go about this is to do a Punnett square. So I brought one down here. Move it up a bit. Okay, so because this is a big Punnett square, I would like to just draw phenotypes in the boxes instead of genotypes. So we'll say if there's at least one big D, phenotypically it would be big D, and if there's at least one big G, phenotypically it would be big G. And let's write the gametes and let's write the proportions of these gametes. So 40% is really 0.4, and that's for big D, big G, 0.4, little d, little g, 0.1, big D, little g, and 0.1, little d, big G. And because you're crossing two F1 individuals, these gametes will be the same on the left. So 0.4, homozygous dominant, 0.4, homozygous recessive, 0.1, big D, little g, 0.1, little d, big G. Okay, so now let's go across. You have 0.4 times 0.4, that's 0.16. And it's going to be big D, big D, big G, big G. So phenotypically, it's going to be big D, big G. Okay? Now the next one, 0.4 times 0.4 is 0.16. And again, because they're getting the big D, big G from the parent on the left, they're still going to be phenotypically big DG. Okay? 0.4 times 0.1 is 0.04. It's going to be phenotypically big D, big G. And again, 0.04, big D, big G. Okay, now for the next line down, 0.16, again it's going to be big D, G, 0.16. Now this is going to be phenotypically little d, little g. and that's because it's homozygous recessive at both genes. Then you have 0.04. Here you're going to be dominant for D and recessive for G. And then 0.04 recessive for D and dominant for G. Okay? Now the next line down, it's 0.04 dominant for D and dominant for G. And that's because the parent on top is giving a dominant G allele. Then you have 0.04 dominant D from left, but recessive G. Then you have 0.01 dominant D, recessive G, and 0.01 dominant D, dominant G. Okay, that's because you get the dominant, the parent on the left, and the dominant G for the parent on top. Okay, finally, the last row, you have 0.04 big D, big G, 0.04 little d, big G, 0.01 big D, big G, and 0.01 little d and big G. Okay, so these are the phenotypes and the proportions that they will be in. However, we want to put them all together. They're saying, what are the expected proportions of phenotypes? So what are the phenotypes you can be? You can be big D, big G. So phenotype big D, big G. You can be little d, little g, big D, little g, and little d, big G. And the two on the bottom are recombinant, and the two on top are parental because there's no crossing over that occurred. Okay, so what genotypes correspond to this? I know they didn't ask for these, but just so we know. To be big D, big G, you need to have at least one dominant allele for both. To be little d, little g, you have to be homozygous recessive for both. To be big D, little g, you have to be at least one big D and two little g's. And then it's the opposite for little d, big G. Okay, so now let's do proportions. I'm going to use a different color to circle each phenotype, and then we'll add them all together. So let's do big D, big G. So we have 0.16, 0.16, 0.04, 0.04, 0.16, 0.04, 0.04, 0.01, and 0.01. So let me just double check. Okay, so those are all the big D, big G phenotypes. And if you add those all together, you will get 0.66. So let me write that here, 0.66. Okay? Now for little d, little g, you have 0.16. And yeah, that's the only one. So you have 0.16 little d, little g phenotype. Okay? Now let's do big D, little g. So we have 0.04, 0.04, and 0.01. And if you add those together, you would get 0.09 for big D, little g. And then finally, let's use black. For little d, big G, you have 0.04, 0.04, and 0.01, which is again is 0.09. So these are the phenotypes in this. So remember, this is the F2 generation now, which came about from an F1 times an F1 individual. So these are all the phenotypes that could be possible in their offspring and the proportions that you'll see them. An offspring of the following cross is test crossed with a little b, little b individual. The offspring data was collected and is shown below. What is the distance between the A and the B loci? Okay, so first, let's look at what the genotype would be for this first individual. So it's an offspring of big A, big B, times little a, little b. And this question is implying that A and B are linked. So the individual from that cross would be big A, big B, little a, little b. And that is test crossed with a homozygous recessive individual. So little a, little b, little a, little b. So let's look at what the parental genotypes from this cross would look like and also what the recombinant genotypes would look like. So for parental, that means that no recombination occurs. Now, recombination can occur in this test cross individual here, but you wouldn't notice because it's homozygous at both genes. So for parental, that means that it would be this big A, big B meeting with a little b. So it would be big A, big B, little b. Or it could be this gamete, little a, little b, meeting with another little a, little b. So it could be little a, little b, little b. Now the recombinant genotypes, those would be the ones that form from crossing over in this individual. And the recombinant gametes would be, if you crossed here, it'd be big A, little b, or little a, big B. So therefore the recombinant offspring would either be big A, little b, because remember they're always meeting with little a, little b, or it would be little a, big B, little b. So now let's look at the data. Of these, which ones are parental? So we're looking for heterozygous at both, so this is parental, and also homozygous recessive at both, so this is parental. And then if you double check, these are the recombinant. So it's asking, what are the distance between the A and B loci? So in order to do that, you want to find, remember that distance for every 1 centimorgan or map unit, that means 1% crossing over. So let's first find the percent recombinance, and then we can use that to get the distance. So for percent recombinance, that equals the number of recombinants over the total number times 100. So if you add the total number of this data is 2,000, and the total recombinants are 200. And then we're timesing that by 100. So that equals 10. So it's 10% recombination, which means a 10 centimorgan map unit between A and B. So for A, the distance is 10 centimorgans, or map units. Okay? Now for B, it says, what frequency of progeny would you expect from an offspring individual of a big A, little b, times little a, big B, test cross with little a, big B, big B. Okay, so again, let's write the genotype of this parent. So we just found out that A and B are definitely linked, and they're 10 centimorgans apart. So the individual that comes from that cross would be big A, little b, big B, and then you're test crossing it again with little b, little b. So when you write it in, this is how we write that the genes are linked. Okay, so it's saying, what frequency of progeny would you expect? Again, let's write the parental and recombinants. So for parental in this case, it could either be this gamete or this gamete, meeting with a little a, little b. So it could be big A, little b, or little a, big B, little b. And the recombinant offspring is if you have a cross here, and that would be big A, big B gamete, or little b gamete. So the recombinants would be big A, big B, little b, or little a, little b, little b. So basically now, because we're doing a different cross in the beginning, the parental and recombinants are opposite from what they were in the first part of the problem. Okay, so now it's asking us, so those are the genotypes that the offspring could be, but what frequency of progeny would we expect? Well, we just found out, remember, that A and B are 10 centimorgans apart, or 10% recombinant. Now when you have 10% recombination, remember that there are two different outcomes you can get from recombination. So if both of these together happen 10% of the time, that means that for each, they only happen 5% of the time because there's two of them. So for the recombinant genotypes, you would expect them 5% of the time. Now for parental, if recombination is happening 10% of the time, that means that it's not happening 90% of the time. And again, there are two different gametes you can have without recombination, so you would divide 90 by 2 and get 45% for each of these. Okay, so that's the expected frequency when you do that cross. Okay, so problem 3 is a little long, so I'd like to diagram the cross as we go through. So it says, a pure-breeding male fruit fly with green-colored eyes is mated with a pure-breeding female with a cream-colored body. All females in the F1 generation had wild-type eye and body color, while all F1 females had wild-type eye color but cream-colored bodies. Okay, so it seems that green-colored eyes and cream-colored body are the mutant alleles because it's saying they have wild-type eye or wild-type body color in the F1 generation. So let's just first define what our alleles are going to be. So remember that in fruit fly genetics, they name the allele after the mutation, and the wild type is plus. So we'll say that G will be for green-colored eyes, but G plus will be for wild-type eyes. Okay? And then for cream-colored body, C will be for cream-colored body, and C plus will be for wild-type body color. Okay. Now, let's do the parental generation for the cross. Okay, it's saying a pure-breeding male fruit fly with green eyes. So you have a male, and he has green eyes, and he's pure breeding, which means that's the only allele he has. So let's just write green for now. And if it doesn't say anything about body color, we're assuming he has wild-type body. So phenotypically here, he is G, C plus. Okay? The female in this parental generation, she is wild-type eyes and has a cream body. So phenotypically here, she is G plus C. Okay. Now, all the females in the F1 generation had wild-type eye and body color. So for the F1, all females had wild-type eye and body color. So wild-type eyes, wild-type body, which phenotypically is G plus, C plus. And all of the F1 males had wild-type eye color but cream-colored bodies. So the males here, wild-type eyes, but they're cream. So phenotypically that is G plus C. Now let's do the F2 generation. Okay, so they have 315 females with wild-type eyes and bodies. So you have 315 females, wild-type eyes and bodies, so G plus, C plus. 324 females with wild-type eyes and cream bodies, so 324 females, wild-type eyes, G plus, and cream bodies. 233 males with wild-type eyes and cream bodies. So 233 males, wild-type eyes, cream bodies. 212 males with green eyes and wild-type body. So that would be G, C plus. 59 males with wild-type eyes and bodies, G plus, C plus. And 47 males with green eyes and cream-colored bodies. Green eyes and cream, GC. Now it's saying, determine how the genes for eye color and body color are inherited, diagram the crosses, and calculate relevant map distances. Okay, So first, let's look at the F1 generation and see if we can get any information about dominance. Looking at the F1 females, you can see that when you cross, for eye color, you cross a green-eyed male with a wild-type eye female, and you get wild-type eyes. So that suggests that wild-type eyes, G+, is dominant to green eyes. Again, looking at this F1 female, if you're crossing a wild-type body male with a cream-bodied female, you get a wild-type body female. So that suggests that wild-type body is dominant to cream-colored body. Now, if those two dominants are true, take notice that we see a cream-colored body in the F1 males. So that suggests that the cream-colored gene is X-linked. So we'll say that that's X-linked. And the reason why we get that is because cream is the recessive allele. So if it's X-linked, then the males are hemizygous and therefore would exhibit this cream allele. Now if you look at the F2 generation, you see that green eyes is only seen in the males, but not in the females. All the females have wild-type eyes, and that suggests that eye color is also X-linked. So say these are also X-linked. And again, that's because males are hemizygous for genes on the X chromosome, and therefore would exhibit this recessive phenotype. So now that we know the dominance relationships and that both genes are X-linked, we can actually write the genotypes for this cross. So let's do, again, the parental generation. So the male, remember that we draw an X chromosome just as a line, and the Y chromosome as a shorter, little, jagged line. So that's the X chromosome. And that first male had green eyes and a wild-type body, which means that he was GC+ on his X chromosome. Now the female in the parentals, they had wild-type eyes and a cream body. Now to have a cream body, you have to be homozygous recessive. And because they were true breeding, that means that they had the wild-type eye allele, or G+, on both of their X chromosomes. Okay, so from these crosses, when you get the F1 generation, the males will get the Y chromosome from their father and the X chromosome from their mother, which is G plus C, which is wild-type eyes and cream body, which is what we saw above. For the females, they would get one X from their mother, G plus C, and the other X from their father, G, C plus. Because both wild-type alleles are dominant to their mutant alleles, this female would be wild-type eyes and wild-type body, which is what we saw above. However, you want to take note now that this female is heterozygous at both gene loci, which means that she can make both parental gametes and recombinant gametes. So if her parental gametes would be G plus C and GC plus. But her recombinant gametes, which would come about from a crossover here, would be G plus, C plus, and GC. Now when you cross this F1 female with an F1 male, it's not exactly a true test cross because the male isn't homozygous recessive for both genes. He only has the mutant allele for body color. However, this sort of cross can be used for mapping because the F2 sons receive only the Y chromosome from the male and are therefore hemizygous again for the X chromosome. So the phenotypes in the F2 males represent the array of parental and recombinant gametes generated by this F1 female, and as well of the frequency of those gametes. So when we look at the F2 generation, we're not going to take into consideration the females, we're only going to look at the males. So let me rewrite these numbers. So you have, again, these are the males. So F2 males, you have 233 G plus C, 212 G C plus, 59G plus C plus, and 47GC. Now looking at the gametes that the F1 mother made, you could see that G plus C and GC plus, these are the parentals. And G plus C plus and GC are the recombinants. Okay, so how do we find, it says, calculate relevant map distances. So again, how do we find map distance? Well, the percent recombination equals the number of recombinants over total. And that's times 100%. So let's see. Recombinants is 59 plus 47. So you have 106 recombinants. And the total here is 106 plus 212 plus 233, which is 551. So if you do 106 over 551 times 100, you get 19.2 centimorgans apart. You really get 19.2% frequency, but remember that each centimorgan or map unit equals 1% recombination. So the total distance between these Ju genes, they're both X-linked, and they're 19.2 centimorgans apart. Question 4. In humans, the C and D loci are linked. Based on the following map distances, determine the probability that the first child between a big CD, little cd woman and a little cd man will have the genotype big C, little d, little c, little d. Okay, so let's first look at what this genotype they're telling us. If you're crossing a big C, big D, little c, little d woman, and you're crossing her with a little c, little d, little c, little d man, what are the gametes that these individuals can produce? The parental gametes for this woman would be big C, big D. So these are parental, and little c, little d. The man here, either parental or recombinant, can only produce a little c, d gamete. However, if there was crossing over in this female, she would get recombinant gametes, which would be big C, little d, or little c, big D. Now the individual they're asking about is big C, little d, little c, little d. And that means that the big C, little d gamete had to come from the mother, and it was a recombinant gamete. So this is a recombinant offspring. Okay. And let's just be clear here. There was another option for recombinants, right? So this individual is big C, little d, but the other recombinant offspring could have been little c, big D. So this is only half, it only represents half of recombination, so just keep that in mind. So for A, it says if the C and D loci are 20 centimorgans apart, what is the probability that this offspring would have this recombinant genotype? Now again, remember that it's only half of the recombinant. So for A, remember that 20 centimorgans apart means 20% recombination. And only one of the recombinants are being accounted for here, so you would divide that by 2, and that gives you a 10% chance of having this offspring. For B, it says now what if these loci are 40 centimorgans apart? And now this is 40% recombinants, and if you divide that by 2, you get a 20% chance of this happening. Now for part C, it says C and D loci are 60 centimorgans apart. Now does that mean 60% recombination? No, it does not. It only means 50% recombination, because remember, that is the max. The range is only from 0 to 50% because when you're independently assorting, the max is 50, or it is always 50% recombination, so that's the maximum you can ever have. So when you divide 50 by 2, you get a 25% chance of this individual occurring. So just keep that in mind. Whenever genes are more than 50 centimorgans apart on a chromosome, they act as if they're independently assorting. Question 5. Genes A, B, and C are located on a chromosome as shown below, with B and C 40 centimorgans apart and C and A 20 centimorgans apart. Assume big A, big B, and big C are completely dominant to little a, little b, and little c. In the following cross, what is the probability of an offspring being homozygous recessive for A and B? Okay, so this problem is asking just for A and B and doesn't care about C. So what is the distance between A and B? If you add 40 and 20, you get 60 centimorgans apart between A and B. Now remember, if two genes are more than 50 centimorgans apart on a chromosome, they act as if they're independently assorting. So in this case, it seems like they are linked. Yes, they are on the same chromosome, but they don't act as if they're linked. So we can do this as a normal problem. So let's write the cross in another way. If this individual, it's written as if they were linked, but let's write them as big B, little b, big C, big A, little a. And this individual is homozygous recessive at all genes. So little b, little c, little a, little a. So this is the cross. And it's asking what is the probability of having an offspring recessive for both A and B. So that we want little b. Again, we don't care about C. And we want little a. So if these genes are acting as if they're independently assorting, what are the gametes that these individuals can make? Now, because they don't care about C, let's not even worry about it. So this individual can only make a little b, little a gamete, because they're homozygous recessive at both those genes. This individual is heterozygous at both genes, so they can make a big A, big B, big A gamete, big B, little b, big A, and a little b, little a. Now, in order to get homozygous recessive, we want this gamete to meet with that gamete to make this. So what are the chances that will happen? Well, this individual can make 4 different gametes, and we only want one of them. So the chance is 1/4 from that individual. This individual can only make 1 gamete, so the probability for that is 1. And therefore the total probability to get homozygous recessive at A and B is 1/4, or 0.25. Question 6. Genes A, B, and C are located on a chromosome as shown below, with A and B 15 centimorgans apart and B and C 10 centimorgans apart. Assume big A, big B, and big C are completely dominant to little a, little b, and little c. A cross between a big ABC, little ABC female, and a homozygous recessive male yields 1,000 offspring. If the coefficient of coincidence is 0.4, how many double crossover progeny will be obtained? So although they give you the coefficient of coincidence, which again is 0.4, this problem is really asking about interference. And remember that because interference equals 1 minus the coefficient of coincidence. And interference is the phenomenon where double crossovers occur less frequently than expected. Well, let's first find what is the expected percent of double crossover progeny. To get the expected, or prediction, you have to use the probability product rule. And that would be the recombination frequency between A and B, and then between B and C. So for frequency, it would be 0.15 times 0.10, and then there's 1,000 progeny. So you have 1,000. That means that out of the 1,000 progeny, we would expect 15 double crossover offspring. Now they're asking, how many do we actually obtain? The formula you have to remember for this is that coefficient of coincidence is equal to the observed number over the predicted number. Okay, so we just figured out predicted, which would be 15, and they gave us coefficient of coincidence, which is 0.4. So if you do 0.4 equals observed over 15, so you want to do 15 times 0.4, and you get 6. So the observed number of double crossover offspring equals 6 offspring. So you want to just remember these formulas because a lot of times it may seem like they're not giving you enough information, but you can actually do simple algebra to find the answer. Question 7. Two genes, X and Y, are located 10 map units from each other. A third gene, Z, is 30 map units from Y and 20 map units for X. So before we continue this, let's just write this on a chromosome where the line represents the chromosome. So X and Y are 10 map units apart. And if you look at Z, it's actually further away from Y than it is from X. So let's draw Y on the far left, and it is 10 centimorgans or map units away from X. Put X here, and we'll say 10 map units. Now Z is 20 map units from X and 30 from Y. So we put Z over here and say that this is 20 map units. And total from Y to Z is 30 map units. Okay, now it's saying, if a big X, big Y, little z, little x, little y, big Z individual is crossed with a homozygous recessive individual, assuming no interference, what percent of the offspring are expected to have a big X, little y, little z, little x, little y, little z genotype? So let's draw that cross using the linkage shorthand. So the first individual is big X, big Y, little z on one chromosome, and little x, little y, big Z on the other. And that's crossed with a homozygous recessive for all three genes individual. Little x, little y, little z, little x, little y, little z. And they're asking, what's the percentage of offspring expected to have big X, little y, little z, little x, little y, little z. So you know that this chromosome can come from this individual here. So let's focus on the other chromosome. How would you get a big X, little y, and little z? Well, to get a big X, that means you have to have this. And to get a little y and a little z, that means you would have to have two crossovers. So that way, you would have big X, follow it down, little y, follow it back up, little z. So if a double crossover happens, that means that the two gametes that will be formed would be big X, little y, little z, which is the one we're interested in. But also, there would be another gamete that would be little x, big Y, big Z. And that's if you follow it the other way around. So if you went little x, follow it up, big Y, and follow it back down is little z. So this is the purple one. Okay, so how do you find, if there's no interference, how do you find the frequency of double crossovers? For that, you use, again, the probability product rule, where you do 0.1 for 10 map units times 0.2 for 20 map units, and that's the distance between the three genes. So you would do 0.1 times 0.2, and that equals 0.02. Now that's the probability of double crossover happening. However, we're only interested in one of the double crossovers, which is this one here. If they ask for total double crossover progeny, then it would be 2%, but we're only asking for one. So let's divide by 2, and you get 0.01. And then for percentage, you just times by 100%, and you get 1%. So what percent of the offspring will have this one out of the two double crossover genotypes is 1%.